Hello Math 2413 students, let's begin lesson 3, the derivative. What is the derivative? Well, that's a difficult question to answer, so we're going to take the similar method as we did in lesson 2. We're going to take several different approaches to visualize several different aspects of derivatives. And the very first is the rate of change. The average rate of change is defined like this: the change of function value over the change of the original variable. So the original variable, say for example time, changes from now to 5 days later. And the change of function value, for example, the price of the stock you're following, is going up by how much or down by how much. Those kind of things are average rate of change. It can be visualized as the slope of secant line, like this. The change of original variable, that's delta x, the difference of x, and change of the function value, that's delta y, difference of y coordinate, difference of the function value. So you can write it as delta y over delta x, or f of b minus f of a over b minus a, like this. This picture says it all. It's the slope of a secant line. That measures the average rate of change. On the average, the change from the red point to the green point is measured like that. Now what we are going to do is to take this green point close and close and closer to the red point. So if I do that, then this secant line will get closer and closer and closer to the tangent line, so that we are going to measure the rate of change at this red point only. That thing is called the instantaneous rate of change. That's something we are going to do in 1.3, but let's be patient. Let's look at this in alternative viewpoint just a little bit. So the average rate of change can be written as f of b minus f of a over b minus a, but here let's take a bit of a change of variable. Let's name h as b minus a, then b minus a, the denominator will become just h, and consequently b is a plus h. Yeah, you see, flip this a to the other side, then b is a plus h. Then this f of b here will become f of a plus h. Do you see the equivalence? Let me expand the font. So h is b minus a, so this b minus a down here becomes h. And then if I flip this a to the other side, b is a plus h. So this a plus h goes in place of b. So we get the second expression. The former is the slope of secant line, yes. And the latter here, that's called Newton quotient, named after Isaac Newton. Some people call it difference quotient, including our textbook author. It doesn't matter which way you call, the name is not that important. In any case, they're the same. Let's see, do we have a visualization? Okay, alright. Same picture, same slope of secant line, same green and red point. Delta x is b minus a. That's the difference of x coordinate. But if I take h as b minus a, then difference of x coordinate is just h. And f of b is replaced by f of a plus h. And then we have the same quantity, rise over run. Rise is f of b minus f of a, or equivalently f of a plus h minus f of a, yeah. And the run is b minus a or h, same. So these two expressions are the same. Same average rate of change, same slope of the secant line, just expressed differently. Now, why did he consider something like this? Well, at times, as a matter of fact, at many times, this quantity is more convenient. Here, a and b looks like they're equally as important, here, h is just supplementary variable. A is the main, and then you can define a function by replacing a by x that way. Am I making sense? I hope I did. If I didn't, then forget about it. It's a bit too pure mathematical. At this moment, everybody should know these two are equivalent, the same. And then as for defining the derivative function with the latter expression, if you can follow, that's great, but if you don't, never mind. We're going to use the formula approach for most of the time. Okay, we are ready now. Average rate of change, we discussed those, and then the Newton quotient, some manipulation, all right. Now here comes the instantaneous rate of change. If this h goes to 0, or in other words, b minus a goes down to 0, then we have a limit. That limit is the instantaneous rate of change, which is visualized like this. We have a bunch of slopes of secant lines here, and the same red point here, and green point is getting closer and closer and closer. Consequently, the green line, the secant line, is getting closer and closer and closer to this tangent line, the red line, and the slope of these green secant lines will get closer and closer and closer to the slope of this red tangent line. And the limit, that's defined as the instantaneous rate of change, or the derivative. Here is the animation. Let's see. Yeah, let's move. Closer and closer, closer, and then, okay, green line disappears, and we have highlight instantaneously, and then we just have red line only. Let's stop this. Okay, right here. We just have red line. Okay, all right. No more of that. So we went through the idea of rate of change, and we're going to use this idea to define the derivative. Do I have enough time? Probably not, so let's stop here. Let's define the derivative in a separate video.